Today we have introduced alternating series. Basically, alternating series. First, we have the signs are alternating: positive, negative, positive, negative, or negative, positive, negative, positive. As long as the signs are alternating, negative to sign, negative to positive, then it's alternating series. Okay. And the second one is the first thing, you have to be alternating series. Second thing is the series must be decreasing. The an plus 1 must be less than equal to an. Then the series will converge, right? Let's see where I can find it. Okay, as we give an example of 9 point. Okay. So alternating series, first given alternating series n from 1 to infinity, negative 1 to power n is the sign of the series, positive, negative, positive, negative, right? Okay. Alright, so this one will converge first. The limit n goes to infinity, an equals 0. Second, the an plus 1 must be less than equal to an for all n, which means this is a decreasing series. Okay, monotonic decreasing series. Then it converge. Then n from 1 to infinity, negative 1 to power n over an converge. So we did prove it yesterday. How do we prove it? We can continue. Yesterday we got S2n equals A1 minus A2 plus A3 minus A4 plus A2n minus 1 minus A2n. So the series S2, S4, S6, S8, S10, S12, continue. This is a sequence. S2 is the first term of a sequence. You can say this is the B1, this is the B2, this is the B3, this is the B4, this is the B5. Okay, continue. This is the Bn. Well, we look at S2n, we consider that as a sequence, not a series. S itself is a series, it's a summation. But we put S2, S4, S6, S8, this separately, there's a new sequence. Okay, then B is a sequence, it's not a, we can look at Bn, this is a sequence, it's not a series. We don't consider that as a series anymore. So look at the sequence. B1, B2, B3, B4, B5 to Bn, this is the sequence. Okay, so in this sequence, yesterday we have proved that S2n equals A1. Okay, so first we have S2n equals this, right? Okay, so look at this sequence. So S2 equals A1 minus A2. S4 equals A1 minus A2 plus A3 minus A4. Alright, so this sequence is I just say Bn is a non-decreasing sequence. Why is the Bn non-decreasing sequence? Because an bigger than equal to an plus 1, that's what we assume here. An is bigger than equal to an plus 1, which means this is positive, you add something positive. Okay, S6 is going to be A1 minus A2 plus A3 minus A4 plus A5 minus A6. you keep adding something which is positive, or at least 0. So this S2, S4, S6 continue is non-decreasing, or at least non-decreasing, right? It might increase because you all keep adding something which is non-negative, keep adding something which is positive. So S8, you are adding another positive thing, which is A7 minus A8. This is positive because AN is bigger than equal to AN plus 1. So the first term is bigger than the next term. So keep adding something which is positive makes this series is a non-decreasing series. Sorry, my bad. This sequence is non-decreasing sequence. So this is a monotonic non-decreasing sequence. This is the first thing we have, the sequence, right? For a sequence, if it's non-decreasing sequence, and also we need to prove something else. Okay, second, a non-decreasing sequence, also if it is bounded, then the sequence converge. That makes sense, right? Because, for example, if you give a sequence, we're not talking about series, just sequence. If it is bounded at some point, you have an L here. If it continued increasing, well, it converge. Because it never passed that L, it converges to that L for sure. Right? Okay. So now next we need to prove, does this sequence is this sequence have a boundary? Does this one have a boundary? Or is this sequence boundary or not? And we did yesterday, we also proved that S2n equals A1 minus A2 minus A3 minus A4 minus A5. Okay, the S2m equals A1 minus A2 plus A3 minus A4 plus A5 minus A6. You know that, right? Continue. Well, then we can compare A2 is bigger than A3, A4 is bigger than A5. So we know that A1 is subtracting something which is positive thing. So we know that S2n, for sure, it will be less than equal to A1. Because A1 keeps subtracting some positive numbers. This is positive. This is positive or equal 0, at least a non-negative. You're subtracting something which is non-negative, so it must be less than equal to AM. So A1. Now we have A1 is your boundary. A1 is the sequence has been bounded. Okay. Then it is less than this. Okay, it's less than equal to this number. A1 is positive. So first, it's not decreasing, it's increasing. Second, it has a boundary. So this sequence is a converging sequence. Will converge. Okay. So S2m is a bounded, non-decreasing sequence. Okay, and then we have limit n goes to infinity, S2m minus 1 equals S limiting infinity n goes to infinity, S2m plus limit n goes to infinity A2m. Okay, so both will converge to the same. Both will converge to some value, will be bounded with some value. Okay, then this one limit n goes to infinity, A2n equals 0. Okay, so since S2n and S2n minus 1 converges to same limit L, so it follows that Sn also converges. If you look at the picture, I draw a picture here, then it will make more sense to you, because the sequence is increasing, but the sequence is bounded. It's increasing, but it has a boundary on the top. So as long as you continue going, it will approach that boundary or converge to that L. That's what it means. Okay, this is S1, this is S2, this is S3, this is S4, and S2n will converge to one point. So that's how we prove that the S2n, the Sn is converged. That's how we prove that the series, alternating series, converge if the limit goes to 0, the nth term equals 0. The second, an is less than equal to an plus, a is long decreasing. So an bigger than equal to an plus 1. So let's look at next example. How do I apply it? So first, n from 1 to infinity, negative 1 to power n, 1 over n. So first, we check that limit n goes to infinity, an equals limit n goes to infinity, 1 over n. This is just a sign. This is the series, right? The term an. So this equals 0. We have the first condition. Limit an goes to 0. Second condition. Limit, an equals 1 over n. An plus 1 equals 1 over n plus 1. So an is bigger than equal to an plus 1. Okay, an is bigger than equal to an plus 1. Alright, so then we have, by alternating series test, it converges. Okay. The alternating series test, you must first make sure that it is a alternating series. Okay, it's positive, negative, positive, negative. Basically, you have to look at this one if it has a negative 1 to power n. Okay. First, if it's alternating series, then you have checked the nth term goes to 0. Also, an is bigger than equal to an plus 1. Alright, it converges. So next one, I'll give you an example. I'll give you 30 seconds to try it yourself. N equals 1 to infinity, negative 1 to power n plus 1, and n over 3n plus 2. I'll give you 3 seconds, say what happened. No, maybe 5 seconds. I'll call student, tell me if this one converge or diverge. Okay. Alright, so can anyone tell me your answer, please? Excuse me. Do you think this one diverges or converges?
Diverges.
Diverges? Why?
Because the limit is not 0.
Yes, very good. The limit n goes to infinity, the nth term test n 3n plus 2. This equals 1/3, not equals 0. So it diverges. Okay. Next example. N from 1 to infinity, negative 1 to power n plus 1. Whenever you see the negative 1 to power some n, always use alternating series. Okay, n over n squared plus 5. Can you do this one? And try this one by yourself. Okay, so can anyone tell me what you got? Does it converge or diverge? I think I'll call a student. Alright, Taylor, you want to try?
This one converge.
This one converge. Okay, so why does this one converge?
Well, when we add 1, the original one is going to be the bigger value, and then when we use L'Hopital's rule and plug in infinity, we're going to get 1 over infinity.
Okay, so the limit n goes to infinity, so nth term will equal 0. Okay, so it's a limit n goes to infinity, use L'Hopital's rule 1 over 2n. Derivative of 5 is 0, so it is 0. Okay, so this is the first condition. Second condition,
when we add 1 to the n over n squared plus 5, that's going to be less than the original n over n squared plus 5.
okay, so you got n squared plus 5, then this one is n plus 1 squared plus 5, then this is n plus 1. How do you compare this two? How do you know this is decreasing?
Well, the n plus 1 squared on the denominator is going to increase much faster than just the n squared will in the original equation, so I figured that that one was going to be a lot smaller value.
Okay, so this one is bigger than this one. Is not always true for, well, for the first two, is not always true. Let's try it. Okay, see if it's true or not true. So, for example, if n equals 1, is 1 over 6. So this is n equals 2. Let me see. 1 plus 1 is 2. 1 plus 1 is what? 2. Wait. Oh, sorry, it's 3. Wait a moment. So n equals 1, what happened? 1 over that, right? So m1 plus 1 is 2. 1 plus 1 squared, which is 4 plus 5, so 2 over 9. Yes. Now check it out. Common denominator is 18. So this is 3 over 18. This is 4 over 18. Is that right? And this is less than. What do you think, everyone?
It must diverge then.
Okay.
I think it still converges.
Okay, who says it converges? Okay.
I think it converges because the general trend in the denominator is that the n plus 1 squared will increase at a faster rate than the n squared.
Yes. But how do we mathematically prove that? Anyone?
You can set them equal to each other.
And then, okay, we can set up that equal each other. And then what happened? We can set up that equal.
And if you were to solve for n, that would tell you when it's which one was larger.
Okay, I believe n equals something, but which is not an integer. It's not easy to solve it because you can see you multiply this, you will not get exactly the same answer. M times n plus 1 squared plus 5n. You solve this one, n squared plus 5, n plus 1. You may not get an integer. And this is a cubed function. It's not that easy to solve it. Well, yeah, we can solve it by using graphing calculator. Okay, so what do you think? So how did I prove that 1 over n is decreasing, or 1 over x is decreasing? How do I prove that 1 over n is bigger than 1 over n plus 1? Besides, I just compare that, or I just give you a random anything, any function, n plus 2, or just x of x, right? X over x squared plus 1. How do I know if this function is decreasing function?
I think you divided one by the other.
You can divide it one by the other. Yeah, that's a good try. But normally, generally, how do I prove if one function is decreasing function?
Can you take the derivative?
Very good. We can take the derivative. Since you see that trend, that the denominator is decreasing, it's going faster. This trend, this one, okay? So let an equal this one. So you're thinking, okay, n squared goes faster, n is increasing slower. So, well, I think it's decreasing, keep decreasing. So we have to know if is it decreasing or not decreasing. So if we want to prove anything is decreasing function or decreasing, so you can take the derivative. If I let fx equals x over x squared plus 5, so the first derivative equals, because quotient rule. Quotient rule is u over v prime is u prime of v minus uv prime over v squared. So derivative x is 1 times keep the denominator x squared plus 5 minus the denominator, keep that, the derivative at the bottom is 2x. So I got this is x squared plus 5 minus 2x squared. Of the bottom is always positive, I don't have to worry about that. So the numerator is negative x squared plus 5 over x squared plus 5. Okay. Is this always less than 0? Would this be negative always? Or under certain condition? This is less than 0 when what? X has to be bigger than something, right? So if x is bigger than or equal to 3, the reason I choose 3, it must be square root of 5, the equal 0. Okay, square root of 5. But I just choose 3 because the integer, lowest integer. So when x is bigger than or equal to 3, the first derivative is less than 0, it's decreasing. So which means the n of n squared plus 5 is decreasing when n is bigger than or equal to 3. Since the function is decreasing when x is bigger than or equal to square root of 5. Actually, you can do square root of 5, it doesn't matter, okay? You can do 3 square root of 5, whichever you want to choose. But we know that an is decreasing when n is bigger than or equal to 3. We got an is bigger than or equal to an plus 1. Alright? Well, actually it's bigger than. So, the first two terms of a series, it does not really matter that much. Because the first two series does not go to infinity. We only care about after n is bigger than or equal to 3 at that point. In the future, not just two terms. The first two terms don't change anything. If converge, the first two terms converge. The first two terms will not change it too much because first two terms is just a number, right? So from the third term, it converge. Okay, so the whole series will converge for sure. Then from n to 1 to infinity, negative 1 to n plus 1, n over n squared plus 5, this will converge. That makes sense, right? So when n is bigger than or equal to 3, it's always decreasing, and the nth term equals 0. So this is the alternating series, it converges. Okay. Alright, so one more example. N from 1 to infinity, negative 1 to power n, 1 over square root of n. Alright, I'll call a student here to help me finish this. Okay, so Thea, could you please help me finish this one? So first, so we check it. So first we check it. Limit n goes to infinity. 1 over square root of n. This equals n goes to infinity. Square root of infinity is still infinity. So 1 over infinity equals what? 0. Okay, that's very good. The first one. Second, I need to check one thing. I want to check an equals 1 over square root of n. Compare with am equals 1 over n plus 1. n plus 1, sorry. You can use the derivative. You can use derivative to prove it. That's fine too. You can do derivative fx. You can add fx equals 1 over square root of x, and f prime of x is equals x to negative 1/2. The f prime of x equals there. Oh, derivative. So you first bring down that first one times x to negative 3 over 2, right? Is this positive or negative? Negative. So this is decreasing. For sure, it's bigger than an plus 1. So now I have first nth term equals 0, alternating series. Second one, an is bigger than equal to an plus 1. So then we got this series here. Converges. Very good. So this one converges. Alright, very good. Okay. Perfect. Alright, so one more example. I need to give you maybe 1 minute to do this one. Try this one. Give you 1 minute. Okay. ln n plus 1 over n plus 1. I think some students have got it finished there. Alright. I would like a student to help me to finish this. Let me think. I'm going to call a student here and help me finish that. Matthew, could you please help me with this one?
Would this series converge?
Yeah. So how do you got it converge?
I did limit as n approaches infinity of natural log of n plus 1 over n plus 1, which equals the limit as n approaches infinity of 1 over n plus 1 over 1.
Okay.
Derivative,
Yep.
which equals 0.
Perfect. Second, you have to continue another condition, right?
So, that's about where I was at.
Okay. So, can anyone tell me what you got after this? How do you prove that this is negative? Have you finished that? Maybe, okay, Zijian? Fx? Oh, and x plus 1? Of x plus 1, very good. Then, equals? Okay. Okay. Okay, that's very good. So you simplify that equals okay, then what do you got? Less than 0 when not always when x is greater than what number? How about I change the 1 into L and E? So L and E. Because 1 is L and E, right? And how about I give you a little bit of help? F prime of x equals x plus 1 squared. This is subtraction, so you can change that into... Okay, so this will less than 0 when what happen? When the Ln function is negative when e over x1 plus 1 bigger than 1 or less than 1. Bigger than 1 or less than 1. Because if it equals 1 is 0. Right? So is bigger than 1 or less than 1? If this is negative. Anyone? Is it bigger than 1 or less than 1? Less than 1, very good, okay. So whenever this is less than 1 is negative. Because you have Ln 1 equals 0, Ln E equals 1. Ln 1/2, this is negative number, okay, this for sure is less than 0. So whenever I have x plus 1 is greater than e, x is greater than e minus 1, or x is greater than 1.7. So basically we can safely choose n bigger than equal 2. Okay? So when n is bigger than equal to, the an is bigger than an plus 1 for sure. Okay? Because when x is bigger than 1.7, it's a decreasing function. So that series is decreasing series. Well, you just need to prove that the first derivative is less than 0, right? Then, if it's decreasing series and also n term equals 0, So the series converge. Okay. Then we have from n from 1 to infinity, negative 1 to the power n plus 1, ln n plus 1 over n plus 1 converges. Alright, which is very good. Okay, so next we can continue looking at the alternating series remainder. I think everyone is pretty good so far with the alternating series convergence test, right? First, you check the nth term equals 0. Second, you take the first derivative of the function. Check that the first derivative less than 0 is decreasing series and it converges. Okay, so we have several examples. That should be enough. So next, I want to look at the alternating series remainder. Okay. So what is the alternating series remainder? If a convergent alternating series satisfies the condition am plus 1 less than or equal to am, the absolute value of the remainder Rn involved into approximating the sum by Sn is less than or equal to the first negative term, that is, okay, the remainder theorem is S minus Sn equals the remainder Rn less than or equal to am plus 1. Okay, so this is the remainder theorem of alternating series. Alright, what's the meaning of that? It means that the remainder is less than or equal to the first negative term. So first the next term. Okay, so let's look at an example. Approximate the sum of series by using the first 6 terms. Okay, for example, we look at n from 0 to infinity, negative 1 to the power n, 2 n factorial. First, we need to check that. We know this is very easy to prove that limit n goes to infinity, 2 over n factorial is 0. Just a very simple thing, 2 over infinity is 0. Second, 2 over n factorial is bigger than 2 over n plus 1 factorial for sure, because the denominator is increasing same numerator. So this one converge. That's very easy to prove. So next we want to prove what does this series converge to. Okay, so what we have, we can prove that because of the series of this theorem, we have the S is the whole series converge point, S minus S6. Okay, so equals R6, which is less than or equal to A. Can anyone tell me what do you have? A what? From this equation, so n equals 6, so A what? Please press the button. A7, very good. Okay, so if I use S minus S6, the first 6 terms is less than or equal to A7. Alright, so basically I got S minus S6 less than or equal to A7. Can I find A7? Yes, I can. Can I find S6? Yes, I can. Both is just a limited terms, right? A7 just when n equals 6. Okay, so I can find A7. A7 is negative 1 to the power 6, because the first term is n equals 0. The second term is n equals 1. So seventh term is n equals 6, and 2 over 6 factorial. So A7, I can find it. It's given 0.0027. Can I find S6? Yes, I can. Okay, so I can find S6 equals, you just add all the first 6 terms together. Okay, and from n from 0 to 5, to -1 to power m factorial. The first 6 terms. So the first term is -1 to power 0, 2 times 0 factorial. Second term, -1 to power 1, 2, 1 factorial. Third term, -1 square times 2, 2 factorial. Okay. Fourth term, plus 3 factorial, -1 to power 3 times 2. Fourth, 1, 2, 3, 4. Fifth term is 4 factorial, -1 to 4 times 2. Sixth term is 5 factorial, and -1 to power 5 times 2. So basically I can find out first, second, third, fourth, fifth, sixth. So add all 6 terms together. You can use calculator. Find these numbers is 1. This first one is 2. Wait. Okay. So 2 over 1, which is 2. This is 2 minus -1, so it's 2. 2 minus 2 plus 2 times 1 is 2. Over 2 is 1. Plus this one give you 2, this one give you 2, this one give you 1. This one 3 factorial is 6. -1 to power -1 is a -1. -2. This one give you this. So this one 4th factorial is 24. Positive 2. The 5th factorial is 120. And this is -2. So now I got my answer is 0.7333. Okay, I find S6, I find A7, so I can estimate the series converge to which point. I can plug everything in. I got S minus 0.7333 less than equal to 0.0027. So can anyone tell me what do you think the S, how do I solve this inequality? So S is less than equal to what? Bigger than equal to what? Anyone? Okay. So I think this is if you use the less than a, so x less than a bigger than -a. Okay. So now if I solve this, is you can use the this formula. We got s minus 0.7333 less than equal to 0.00277. Okay. Bigger than -0.00277. So I got s is less than equal to 0.7361, bigger than equal to 0.7305. Basically, I can estimate the whole series converge to 0.73 something. Okay, so it's in between these two values. Okay, it will not bigger than this, but it's in between these two. So this is the way to help you estimate which point does this series converge to. Okay, alright, so this is the remainder theorem for the alternating series. We'll finish tomorrow this alternating series real quick tomorrow. I think spend another 10 minutes finish that. Then we can move on to ratio test. Okay, I'll see you tomorrow. Thank you very much.